Okay, we have a quiz in 2 days, right? All right. And so what we're doing today is finishing chapter 6. And I thought to myself, if I gave one student advice about the quiz, I should give everybody the same advice. That's only fair. And the advice I gave was, approach this quiz in 2 days as if you knew in advance it's the hardest one of the whole semester.
That's not advice.
Huh? It is true. It will be.
It's the hardest one
Of the semester.
I thought the last one was the hardest one of the semester.
Actually, the last one, what happened last one? I don't know.
I got it.
No, stop. It was the hardest one so far of the 2. This one's the hardest, and then it gets a little easier on 4, and then your final, I just take it back. No, it shouldn't be so bad. The final, you know, after I'm going to give you a bunch of hints on that last lecture about the final to make sure you're studying in the right direction. So we're a long ways from there, though, right? We're just a little over halfway through the semester, a month and a half. Month? Yeah, at least. So today we're finishing chapter 6. Are we ready? Hang on. We got an in-class assignment, so we're going to have to move a little bit faster than you may like. The 3 we're doing today, which are not up there, for whatever reason, are assignment model, shortest route, abbreviate there, and abbreviate here too, max flow, maximum flow. Those are the 3. Do most of you at least kind of remember some of the hints I gave you from transportation model and transshipment model? Like, for example, what do the nodes represent if you're writing a linear programming problem? The constraint, very good. What do the arcs represent if you're writing a linear programming model? The decision variables, your variables. You got that? Okay, same thing with most of what you're about to see. We're going to start out, I want you to see something here. This is an assignment. Now, when would you use assignment? Because a lot of people go, oh, this looks just like transportation. It's when you have one thing that has to be done by one source, one-to-one kind of ratio, and you're trying to figure out which one of these should go to which one of those. A perfect example is in a CPA firm. A big CPA firm has a lot of accounting majors with CPAs who have to do audits. So when they get the audits in, they have to be done, they're saying, let's use an assignment model to figure out what would be the best decision as to which auditor would go to which audit. And that may be an example. A law firm, they get a bunch of projects in, they have to assign lawyers to. Which lawyers would we assign to which projects? It's a one-to-one comparison usually, or a leader of a team, which team will represent one group. So in this case, in this example, these are our subcontractors, and one of them each could have the chance to be assigned to one of these 3 projects. There's the one-to-one relationship. But if you notice, there's more suppliers here than there are projects to be done. So this is the situation where one of these subcontractors will not be assigned. And whatever's in the best interest. In our case, you're the manager of the company who's the general contractor on this job. And you're the one who has to assign these subcontractors for this next coming period, whatever it may be. And here are your choices. Now, the only way you're able to save the company money in this particular situation is we have to pay the subcontractors not only a flat rate, but a sum of money based on how many miles they have to drive to the project. So this chart represents the number of miles each subcontractor would have to drive if they were assigned that project. And your goal is to assign the subcontractors to utilize the least amount of miles possible to save that expense. So your first thought is to assign which subcontractor to which project. Name one. Subcontractor. Universal, I heard, to what? C, because it's 14. But then you'll start saying to yourself, now that C's done, Universal's done, we still have all of this to evaluate, which you may go right to the next lowest one possibly. And then we got all these to evaluate. What linear programming will do is take all of that guessing and evaluating out of the way, and will show you exactly the least expensive way to assign these and which one will not get the job. I want to give you a hint. I will not trick you on the quiz. I will not trick you on the final exam. But in real life, a lot of times there's more projects than you have. These are called tasks, and these are called, I can't remember. tasks and assignees, I guess, I can't remember, we'll know in a minute. And if there's more projects than there are assignees, you have to add what's called dummy assignees over here. And you have to have at least the even amount or more, but you can't have more projects. You can't leave customers or projects not being assigned. Of course, when you add a dummy, there'll be one not assigned, but by adding the dummy, this will help you make that decision which one's going to be left short. Now, my question for you is, can every subcontractor go to any project we assign to them?
Yes.
And if a subcontractor couldn't go to an assignment project, what would we see?
Dashboard.
A dash or
NA.
blank or a 0, something like that, trying to indicate we cannot assign this subcontractor to that project. That it will be either a blank or a dash or a 0, something trying to say that's not an option. I'm just giving you a heads up because they don't always have numbers for every one of them. Now, we're going to draw this, just like transportation. On the left side is however many could be assigned to whatever the task is you're assigning. How many nodes would we have on the left side? 4. There are 4 subcontractors. How many on the right side? How many tasks, in this case called what? Projects, and how many?
3.
3. Now, since every one of these subcontractors can go to any one of these projects, I'm going to put arcs to each one of them, just like that. Ain't crazy? Forget that one. Wait, I'm getting confused. Hang on. There we go. Now, look how crazy this looks. It's hard to tell, but my question for you, what's our supply amount?
1.
That's right. We can only assign 1 to one task. What's our demand? 1. This is what's left off most of the time, including the PowerPoint. But these need to be here, these 1s. Because these 1s are telling you what to set all your constraints to. Now, just like transportation, in most cases, this will be less than equal constraints. These will be equal constraints, just like transportation. There are rare situations, though, that these might be equal also, but I'm not going to trick you in rare cases. We're going to stick with what's used most of the time and what you're going to come across most of the time if you are getting into this. All right? Now, all of these would be the numbers of the miles. These are like the cost, but really it's just the amount of miles. What do we got here? 50, 36, 16. My question for you is, remember what the whole objective here is this a minimization or maximization problem? Min, because we're trying to minimize, that's right, the number of miles, which represent kind of the cost that we're going to have to pay. So this is a min. Now, what should we do with these nodes is we should number them just like we did with transportation, no difference. Transshipment, we numbered the nodes slightly different. We didn't repeat numbers. The transportation and assignment, and you're about to see shortest route and max flow, you can repeat numbers in a situation like this. So I'm going to go 1, okay? 1, 2, 3, 4, 1, 2, 3. Now, just like transportation, you actually have all the information necessary to write the whole linear program right now, if I had the time to write all those numbers out. Be prepared, though, if you're given a problem like this, you might be asked to draw the network. Or you might have a network like this, but with the 1s, and be asked to give parts of the linear programming model, not all of it. Maybe constraint for task 3 and constraint for, what do we got here, subcontractors, it's called subcontractor 1. You might write 2 constraints. I'm looking to see that you know to make this one less than equal to 1, you know to make this one equal to 1. And when we're writing the constraint for a node, how do we know how many variables will be on that constraint? You don't remember from transportation and from transshipment and from shortest route you're about to see? How do we know how many variables? Let's go with this top left one right here. Let me do the right-hand side. Help me out. Not all at once. We're recording. How about less than equal 1? Now, how many variables are going to be on the left side? 3. Because 3 arcs touching the node. However many arcs are touching the node tells you exactly how many variables are in that constraint. That makes it easy. And I know we highlight that. Here we go. I'm going to go x11 plus x12 plus x13 less than equal to 1. Let's go to this fourth constraint. Help me out. I'm going to first put less than equal to 1. How many variables are there on the left side?
3.
3, because there's 3 arcs. X, help me out. 4, 1 plus x plus x. There it is. That easy. Let's do a task constraint. How many variables are in the constraint? The third task of project needs to be done right here. How many variables? 4. Equals 1. Help me out. X. 1, 3 plus x. No. 2, 3 plus x. 3, 3 plus x. 4, 3. It's always from where it's coming from to where it's going to, and these order of numbers right here. They got to be in the order where it's coming from to where it's going to. What you're doing is you're saying, if there's 4 arcs touching it, I know there's 4 variables, I just need to figure out what those variables are. You'll definitely, there's a big deal, though at least you know there's 4. You're going to have 4 there, whether they're right or wrong, who knows, but at least you have 4. Now the objective function. How many variables are going to be in that objective function? How many? 12. However many arcs. Every variable is in the objective function with its corresponding number. Notice none of the left-hand side variables have these numbers. The 50, the 36, the 35, the 25. None of them are there because they're all in the objective function, just like transportation. I believe that's just like transshipment too, right? So I'm just going to write some of them real quick. Start at the top. X11, I guess you forgot, put a 50 in front. 30 plus 36, X12 plus 16, X13, dot, 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 all the way down for every one of these. 28, X21 plus 30, X22 plus 18, X23 plus 35, X blah, 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 blah. Right? This is easy. This is the part you're going to find easy. Let me see here. So it should look like this. There's your 12 variables with their numbers. Here's your 4 subcontractor constraint. Here's your 3 tap agents. That's the word I was looking for. Agents. That's the left side. Here is your 3 taps, all equal to 1, less than equal to 1, right? Get it? These rules, these little hints about how to write these are the exact same for transportation. Once you have these down and big highlighted, ready to go, you should be ready for all 3 of these you've seen so far. Oh shoot. Hang on. Which one is this? This is the, let's go here. This is this one, right here. We have, these are backwards. Agents are up top. Tasks are right here. It's back, it doesn't matter. This can be this way. You're still going to get the right answer. Here's your agents. Here's your tasks. Each agent less than equal to 1. Each task equal to 1, right? This is the 3 right-hand sides. Most of the time, your agents will be on the left side, but it doesn't matter. It doesn't matter. This is still, as long as you stay consistent. All right? This is your objective function. Should we? Yeah. Okay. You ready? Let's solve it. Do the numbers look right? The 50, the 28, the 35, 50, 36, 16 going down. Are these 3 right here? And these 3? Help me solve it. Help me remember. Data. Then what? Solver. Oh, look at that. There's no numbers in it. Perfect. What goes in set objective? F13. Very good. Probably supposed to be with dollar signs. Max or min? Changing variable cells. Where are the cells where the answers are going to appear? Oh, don't even give me that sign.
F16 to I.
That's 16, 17, I think. F17 to I.
20.
19, I think.
19?
Yeah, I think you only got 3.
Yeah,
19. So, very good. We're going, I already forgot it. Darn. F, what is it again? 17. F17 colon.
I-20.
I-20. Was it? Is that true?
I-19. Sorry.
19. Okay, did I use a colon or is that a semicolon?
No, that's not 189.
Thank you. Is that a semicolon or colon? We'll see if it works. All right, now we got to do constraints. Add. Anybody remember? Cell reference. Any of these. Let's do the equals first. Let's do all three of them. These cells have to equal these cells. There's those. I'm going to add. These cells have to be less than equal to these cells. Let's take a look. Because I have like equalities, we have three of them that were equal signs, so I did all three at once. Or you could have put J17 equals L17, J18 equals L18. You could do all three separately, and I just combined them. Then there were four of them with less than equal, so I combined those also. I got to click a box, right? Make this one right here. And then I got to change this. Boy, this could have been set up better. Here we go. My question for you is, who is going to be assigned to, I don't know, I'll show you that. What was this? This is the 14-mile one, right? Whatever this one is. This is the 14-mile. I want to know who got assigned there. Because when I asked you, you said it would be Goliath or something, which is this bottom one, right? 4-3, we thought would be one of the assignments. And I don't think it is. In order to save mileage, it ends up being where? 4-2. Say it again.
4-2.
4-2, that's right. That last subcontractor is going to go to Project 2, which was not the 14 miles. And where is Agent 3 going?
Nowhere.
That's the one not assigned. Agent 2, that first task up here, and then Agent 1's going to the chief, the one down there. So it's also interpreting this. Okay. All right. How many miles are they going to have to pay these subcontractors altogether? 69. And that's the lowest amount of miles. There may be another way to assign these, possibly, but you're not going to get below 69 miles. That's as low as it's going to get, even with an alternative answer. So you might as well run with the one you have, unless Agent 3 has a special reason they can't pull it out. All right, next. You're done with assignment now. It's that easy. Everybody have all their notes ready? Okay, similarities, but there's some differences here, and this starts to get people the real biggest differences. This is called shortest route. This is where you're planning out logistics again, and logistics says our trucks could take this route, this route, this route. They have all this in the system. They're checking every possible route to see what would be the least expensive way to have our goods shipped on all these trucks. Now here's the deal with shortest route. I want to make sure I got everyone's attention. I don't want anyone to miss this. Anytime there's an arc between two middle nodes, not the beginning, not the end, two middle nodes on shortest route, it goes both ways, and it's really two arcs. Let me say that again. It goes both ways, and it really represents two arcs, which means it represents two variables, not one variable. For example, look at the arc between 3 and 5. There's no arrows there, just an arc, and because it's the shortest route, and because it's between two middle nodes, it is really two routes, x35 and x53. And they're both up two variables, even though it looks like the same exact route. And usually, where you see these letters, almost all shortest route problems have numbers there on how much it might cost, on how many miles it is, whatever it is that's in the story that represents what makes you decide what the best decision would be, those numbers are on there. This particular problem, though, you had to calculate those numbers. Now, let me show you.
Can you repeat that, please?
Which one? The whole thing.
The rule, yeah.
Okay.
Wait, but isn't 5 like an end node?
No. Here's the end. The largest number's always the final destination. The 1 represents where everything's coming from. You know, now that we're back on this, I do want to mention an additional item. I said all the middle node arcs go two ways. Any arc touching the end and beginning are only one-way arcs, period. So everybody get that? That's what makes this confusing. You can't visually see the difference. You got to know this rule. Anything touching the end, all of those arcs right there, they're one ways. And they're going from wherever they come from to the end. That's it. Once you're at the end, you can't go back. It's one way. At the beginning, every one of those arcs are one ways. Once you leave the beginning, you don't go back. But you can leave and go to any middle arc, go to another middle arc, go to another middle arc, go back to a middle arc, go back to another middle arc before you get to the end. But once you get to the end, that's a one way you just go. Good job.
What's the difference between the lines? Because it looks back here that some of them are like
Dash? No, that's just, it doesn't mean to be dashed.
Oh, okay.
Ignore that.
All
I
right.
think that's just, who knows?
I think it's just the error, because on our PowerPoint here, it shows it regular.
Yeah, and look how this one looks kind of spin. Is that my eyes or does it look spin to you?
No, that does.
Yeah, it's just this, who knows what it is. It's not meant to be dashed. They're all supposed to be solid lines. Go, Jacob.
When you say middle, you mean like 2 through 5?
2 through 5. 2 through 5. But if the arc's going from 2 through 5 to another 2 through 5, then it's two ways. Unless there's arrows on the arc trying to express that this is not a two-way, it's a one-way. That's possible on some of the shortest route problems. Everybody hear that? See this arc going from 3 to 5? If it has an arrow right there at the end, it's trying to tell you, even though this is shortest route, that's a one-way. It's not a two-way. But when you just have a line on shortest route going from a middle arc to a middle node to a middle node, it's two ways. Now here's the tough part. How many variables do we have? I mean, do you see how we got to count this? 1, 2, 3, 4, 5, right? And they're one ways. And then we have 1, 2, 3, 4, 5 one way. So there's 10 variables. Now, let me get some, here we go. These are two-way, so there's 10, 11, 12. Two-way, 13, 14. Two-way, 15, 16. Two-way, 17, 18. Did I miss them? I think that's 18 variables. So there's nothing from 2 to 3 there. That's what I was looking for. So that's how you got to count this. So you help me out. What is this variable right here? X, 2, 5, and X? You got it. X, 2, 6, and X? No. That was trying to get you to, huh? No. X, 2, 6, and that's it. It's a one-way. Once it gets to the end, it's a one-way. There is no other variable. You guys got to see that. I tricked you. All right? How many constraints are there? However many nodes. That doesn't change. Just like transportation, just like assignment, just like transshipment. However many nodes are constraints. I want to write a constraint. So you can see that this has a lot of similarities, even though it has those slight differences. Let's write a constraint for node 1. Now, almost forgot one more. Before I even get to the story, every constraint on shortest route, if it's a middle node, is equal to 0. If it's beginning node or end node, it's equal to 1. Everybody hear that?
No.
All right, ready? Assignment problems. Coming out of the beginning, this constraint for this node is equal to 1 because it's the beginning. This one at the end is equal to 1 because it's the end, destination. But all the middle node constraints are equal to 0. And the reason is, just like transshipment, whatever goes into a middle node has to head back out. Nothing stays. Just like transshipment, nothing stays in those middle distribution centers. They head right back out after they get, put in their different shipments. So again, equal to 1, the rest are equal to 0. We don't even know the story, but we can write a constraint with just what I just told you. Again, let's do constraint 1. What's the right-hand side?
Equal to 1.
Equal to 1. Thank you, Justin. Now, how many variables?
1.
Oh, stop. How many variables? On constraint 1. 5 variables. Here we go. Left-hand side. X, 1, 2, plus X, 1, 5, 3, whatever, plus X, 1, 3, I heard, plus X, X, 1, 4, plus X, 1, 6. There it is. There's the constraint for the first node. This is node 1. Okay, let's go to node 2. But now that we're on a middle node, whatever goes in has to be the opposite of whatever goes out as far as being positive or negative. And once you decide which is positive, which is negative, you have to be consistent through every middle node. Go, Justin.
So, no, 2 through 5 are middle.
That's right.
Okay.
So now we're going to write a constraint for 2. And we have to decide whatever arcs are flowing into 2 are either going to be positive or negative. Whatever arcs are flowing out of 2 have to be the opposite. And once we decide what that combination is going to be, we have to be consistent for every middle node. Because the last node is just like the first node. They're all positive and equal to 1. But these, you have to have whatever goes in heads back out. So we got to have positive, negative mix. So let's go with node 2. Let me start with the right-hand side for node 2. What's it going to be? Equal to 0. All right. Now, this side, how many variables do you see? 4. Come on, wait a minute. I see 1, 2, 3, 4. 4. Well, how many arcs are touching it? How many? 4. 4. Because this arc is a two-way. It head out and is coming back. That's why there's 4 variables, because that one's going to another middle node. So we have x, hang on a minute, x1, 2, x, what do we have here? X, what's going to 2 though? X, 5, 2, and then we have x2, 5, and then we have x2, 6. Okay. So these are going into 2, these are going out of 2. What do you want to make negative? What do you want to make positive?
The first one's positive.
Positive. So a positive 1, 2 plus 5, 2 minus 2, 5 minus 2, 6. Okay? Positive, positive, negative, negative. Now that we decided which are positive, which are negative, we have to be consistent for every constraint in the middle node. Jacob, you have a question? Why is it what? Is the one leaving 2, because we're writing this for this. For this is node 2. So what's happening with node 2? That arc's going from 2 to 6. It's not coming back. And we made the ones that are going into 2 positive, and the ones leaving 2 negative. So since that one is leaving 2 going to 6, this is the end. That has to be negative. Just like the one now going from 5 to 6 is going to have to be negative when we're writing the constraint here. When we write this constraint, you're absolutely right. 5, 6 is positive. 2, 6 is positive. They're all positive on the end and the beginning, but not in the middle. You have both positive and negative, whichever order you decide to go in. Let's go to constraint 3. Constraint 3. What's the right-hand side? 0. Equals 0. How many variables are going to be in constraint 3?
5.
6.
Let's take a look. 1 and 2. Those are the only single one-ways, right? Because it's going to 6, it's coming from 1. So 1, 2, 3, 4, 5, 6. Right? You ready? And we're positives going into node 3. So I've got x1, 3 plus x.
3.
Thank you. 5, 3. Oh, the other 4 are negative? No, there's 4 positive. What else we got?
4, 3.
Thank you. 4, 3. Okay, now they're negative, right? Negative x3, 5. Negative x3, 6. Negative x3, 4. Doesn't matter what order you put them in, by the way. As long as you got the negatives and the positives consistent all the way through, it doesn't matter what order you put this in. I could have started with a negative 3, 4 plus 1, 3. That doesn't matter. As long as you have the negatives and positives correct. We good? Do number 6 real quick. Let's do 6. Ready? Equals.
1. Sorry.
How many variables are there?
5.
Oh, thank you. 5 variables. Because they're all one way, there's 5 touching 6. These are all going to be positive, no matter if they're coming or going, because this is a one-way node. And I see, we have one going all the way from 1 to 6? So this is node 6, right? x1, 6 plus x5, 6 plus x, what do we got there? 4, 6 plus x3, 6 plus x, what is it? 2, 6. I didn't do 2, 6. There they are. That's it. Let's go to the story so you can see how this all gets put together. The story is, you've got an employee that needs to get to this conference. Your goal as the manager is to get this employee to the conference at the least expensive way possible. All right? So you have to take into consideration all the different routes and all the different forms of transportation and all the different costs associated with these routes, including however much time that she's going to be subject to get to this conference. We have to pay her $15 an hour. So that's part of the cost. If we get her there short time, the transportation may be more expensive, but we're saving $15 an hour. So you got to take that into consideration. Here is every possible, what were the letters? A through M, it looks like on here. So there's A through M, what they represent. Route A, let's just look at it real quick. That means she's leaving our company headquarters, going to this first location, that's what Route A is. And Route A is taking a train, it's gonna be 4 hours, which will cost us how much just for her to be on the train? That's right, 15 times 4, $60, plus the $20 cost of the ticket. So that total there would be 80, is that correct? I go to the next slide, look. Yeah, $80. So each one of these, you go down and you say, Form B, which you have to take a plane, it's only 1 hour, but the ticket's 115. Another 15 out of that for her time takes us to 130. Same with the bus, 2 hours, there's the tickets, $10. Her time would be $30.40. And here they are for every one of the letters. Now these numbers are what would be on the drawing for shortest route. Just like looking at page, I wanted to show this example. I think this is shortest route, let me look. This looks like shortest route, right here on page 300. Now these have arrows in them. Man, there we go. Top of page 304, that's got to be shortest route. So they look like that with the numbers on it. Yeah, that looks really very similar to what we're doing, doesn't it? Except for 3 and 4 don't look the same for the rest of them. All right, so whether you're given a drawing or whether you're given a story with, and if you're given the drawing, those numbers would be on the arts. You could come up with the objective function. Can we come up with the objective function? That's the only thing we didn't talk about. We know it's going to be every arc and the cost related with that arc. That would be both for time and the ticket. But here's the deal. Let me go back to this drawing. Do you see this arc right here? This represents 2 variables. Whatever that cost is for F, it's got to be in the objective function twice, with the numbers 2, 5, and then the numbers 5, 2. So look at this objective function. 60x52, 60x25. That's a 2-way. It's got to be in there twice with the cost, whichever direction, because we could be taking the employee to node 5 back to node 2, then to the destination. It could be either direction. Look at, where's another one that's 2. Here we go, 3, 4 is 2 middle nodes, so there's got to be a 4, 3. There it is, 4, 3. So middle node, so that's why you have, how many did you say total altogether, 18? So there should be 18, or was it 12? Was it 18? 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I don't know where we got 18. 17? Everybody get it? Let's make sure you get it. So I look at this, 3, 4, how about this 4, 5? Whatever that cost is, there's going to be a variable 5, 4 with that same cost. So there'll be 2 of those, 4, 5, and 5, 4. Can you write the objective function with this information? 5, 4, 4, 5, both 50s. All right? Everybody got it? So now, we know she's got to get there. We looked at all the alternative routes and all their costs. We set up our objective function and all our constraints. Real quick, so constraint 3, is that how many they have? 1, 2, 3, 4, 5, 6. 6, good. So we got that. We plug it into the computer, and here's our output. My question for you is, when our employee leaves the home office, what node is the employee going to first? Which one? 3. 1 to 3, that's right. So right here, we've just went from here to here. Our cost so far is C. C is a bus. She's on for 2 hours, $30 for her 2 hours, plus the bus ticket for 10. We're $40 into this now. All right. Now, once we leave 3, where are we going? 4. So 4, we went. What letters from 3 to 4? H. So we took a taxi. This is crazy. A taxi for an hour. I don't know. You guys have had to live in a taxi, haven't you? All right. $15. $15 is 5 minutes in a taxi. I don't know where they get this. An hour in the taxi, $15 for the ticket, $15 for her time. There's another 30. What's that put us at? About $70? Okay. So now we're going from 4 to where? Is it 5? Okay, so 5 is letter, what is that? That's J or I? It's I. Is it I? A train, 2 1/3 hours. Per time, $35. The train ticket, cheap, $15. There's another $50. And then the last part of the route would be obviously from 5 to 6. Is that correct? Which is letter M? No. L. L, taking a train, another train, for 1 1/3 hours, $20, $10 for the ticket, $30. My question for you is, how much is it going to? What's the least expensive cost involved getting her to this conference? $150. It may be an alternative route, but it's not going to cost less than $150. It'll either be equal or more. But so we might as well go with this route. All right? Oh wait! Oh wait! Oh wait! Oh wait! Oh wait! Wait 1 minute. Here we go.
Okay.
It's the shortest route.
Yep.
All right? What do we got here? All the variables, x, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Notice this. 2, 5, 5, 2. 2, 6, 3, 4, 4, 3. 3, 5 was 5, 3. 3, 6 is the end. This is the 4, 3. 4, 5 is the 5, 4 right there. 4, 6, 5, 2, 5, 3, all the way across. 1 at the end, 1 at the beginning, zeros, these all the way down. These are all equal signs. Here's our objective function. Here's where our optimal solution will show up, right? Here are our costs. 80, 40. I want to get one in the middle here. Here's a 2, 5 at 60, so 5, 2 should also be at 60. Here's a 3, 4 at 30, so 4, 3 should also be at 30. Get it? You ready? Solve it. Data. Solver. Is E18 the correct place for the objective function? Justin's not here to tell us. Is the cells being changed happen to be, what do we got here? E16 through U16. Does that look correct? These are all equal, so they're all grouped together at E21. Is that correct? E21 to E26 equal to V21 through V26. The box is checked. Simplex is the, now this route could be different, but the cost should be the same. This could be an alternative route. What is our route? We're leaving node 1, going where? Huh? Why did you do that? Okay, we're leaving node 1, going to which node? 3. Now that was not the case before, was it? Wasn't it 2?
Yeah.
It was? Okay. We're leaving 3, going to what?
4.
Is that also safe?
Yes.
4 to 5 then?
Yes.
5 to 6?
Yes.
Is the cost the same?
Yes.
$150? All right, you can solve this, right? So send her on her way, book the 2 train ticket, get the taxi, tell them you want also to borrow that taxi when she's done with it, because you can't leave the price. You guys, you've never rode a taxi? It's like 5 minutes is $20.
Yeah,
Oh my God. I mean, with tip and everything, it's like $20 for a 5-minute ride. I'd rather walk. I'm too cheap. All right, we're on the last one. There it is. Let's start with similarities to all the other 4 we've learned so far. Every node is a constraint. Every node is a constraint. There's similarities. Every arc is a variable. Similarity again, right? Similarity. Here's a difference. In shortest route, these were all equal to 0, and this was equal to 1 and 1, the beginning and end. In max flow, they're all equal to 0.
Everything?
Everything. I mean, every constraint. Every node's constraints equal to 0. Now you got me questioning it. I gotta look. Yes. Whoop, hey, stop. Ready? Every node is constrained, every arc is a variable, and every constraint's equal to 0. How many constraints do we have? That's right. Arcs on max flow almost always have arrows because some are 2-way, but they may have different costs. Some are 1-way. So on max flow, you don't have to worry about are these a 2-way or 1-way. They almost always have arrows to tell you which way it's going. Where do I start? I always say the very first thing you should do, so you don't get confused.
Okay.
I joined the circuit after class. The circus and jungle erasers. You ready? What did I just say? The first thing I would do first thing, so you don't get confused, once you say, okay, this is a max flow problem, which, by the way, this is used very much by municipalities who want to find the best alternative routes when they have to do construction projects. This would be an example. Or, and matter of fact, when we read this story, a lot of shipping companies will use these because what if one of our trucks break down, or what if one of our planes break down? We have other planes or other trucks going in different directions. Do they have excess room to load packages in case one of these other trucks or planes break down to still get the packages to their end destination? So we can, satisfy what we promised our customers we would do in what time we said we would do it. That's when these are used, all right? And in this example, it happens to be a plane shipping company that uses planes to get things around the United States. And this isn't, what they're doing is they put it together, and this is real true. Emergency plan in case a plane breaks down. We have a plan in place. You don't have to sit there and panic. You go to the plan. Okay, if that plane breaks down, here we know there's going to be excess capacity on these other planes that are going opposite directions, which go to hubs, which will then take the packages onto other planes, which could still get them to their eventual place. It's just a little more costly, but we got a broken down plane. And so they have the plans in place. This plan that you're about to see is if a plane breaks down in San Diego. But they would have a plan in place in case this plane breaks down, or that plane, or that plane. Or there could be multiple planes. There's obviously 3 shipments going out of San Diego. So we want to know what happens if there's 4 actually. And the plane that's breaking down is going from San Diego to Tampa. But this company would have a plan if the plane breaks down going from San Diego to Denver. This company would have a plan if the plane's going from San Diego to Dallas. Every possible situation, there's a plan in place using this kind of linear programming to make sure they're prepared. That's all part of management. So, you ready? The first thing you do with max flow is you have to add an arc that does not exist. And you're adding an arc that goes from the end all the way back to the beginning and put an arrow. What max flow does is says, we're trying to figure out what the maximum amount of whatever it is happening here that needs to get there that can get there. And this arc represents that maximum. Because once all this happens, everything ends up going here. And we're going to pretend as if it would leave here and come back, even though it really doesn't. That's how linear programming then will calculate how much would be available to leave. That amount available to leave is the maximum amount that could go through this backup plan. So if we end up with, this is shipping for packages, and it's probably based on cubic square feet. So if this ends up being 9 or 9,000, then we know that the most we're going to be able to ship out of here is 9,000 to get it to Tampa with all these alternative routes we're about to find out. Our answers telling us the alternatives to get it there. And the maximum we can do to get it there. That's what it's going to tell us. So here's the weird part. You're used to putting every one of these arcs numbers in an objective function. You can't do it with max flow. Max flow that's the main difference, is the objective function doesn't have every variable with its number. It only has one variable, and the variable is the arc you drew from the end to back to beginning. So in this case, our objective function, which max flow literally tells you basically what your objective function is. Max, whatever. The arc we just drew. X, 7, 1. The arc coming from the end to the beginning. That's your whole objective function. Nothing else is put in your objective function, which creates a problem because these constraints are written exactly like all the other models. Let's go 5. All right? This is equal to 0, just like I told you every constraint is for this problem. How many variables will be in this constraint, number 5, that's equal to 0? How many variables? Oh, stop. Is there 5? 1, 2, 3, 4. Okay, just checking. Right. 5 of them. Are you ready? The same plus minus situation. You have to decide right now, do you want the ones coming in? I guess we'll stay consistent. We made the ones going in positive, the ones leaving negative, and we'll stay with that for now. Okay, but you can switch it, but you've got to be consistent with every node. Every node will have both positive and negatives. Not like shortest route where the beginning and end are all positive. Every node has positive and negative variables in this problem. Every one of them. So, what's going into node, what is this, node 5? We got x25 plus x, help me out. What's going into 5?
4, 5.
4, 5. Is there anything else going into 5?
No.
So now we have minus x5,
2.
2. Minus x5,
4.
4. Minus x5,
7.
7. Is that it?
Yes.
Equals 0. That easy so far. Here's the hard part. You ready? Let's do node 7. Wait, which one's this? 5? 4 or 5? 5. Let's do node 7. What's going into 7? X?
5, 7.
5, 7 plus x?
4, 7.
4, 7. Any others?
6, 7.
Plus x, 6, 7, minus x.
7, 1.
Very good. Wait, is that on the PowerPoint? All right, I was too fast. 7, 1 equals? That's it. That's the only arc leaving it because you're adding an arc from here. Let me add it. You're adding an arc from here to there, and that's leaving. Let's do node 1 since you guys are on the ball here. Node 1 going into node 1.
7, 1.
X 7 1 minus x 1 2 minus x 1
3,
4 minus x 1.
3.
Is that it?
Yep.
Is there another one or not?
No.
Equals the objective function, one variable only. It's the arc you drew, and these all follow the same rules as transportation, as assignment, as transshipment, same exact rules. Now here's the deal. You ready? What about these numbers? Look at all these numbers. They're not in our objective function like every other problem. You have to write a constraint to identify these limitations for every single arc. This is the only one you got to do what's called arc constraints. Are you ready? First of all, how many arcs have numbers on them? This one is not, you don't have to write a constraint for it. It's the objective function, and it has no number with it. It's the number we're going to get here that's going to tell us. But how many do you see there? Like a lot, right? 17 of them? So, let me start with x1, 2. You ready? x1, 2 has to be less than or equal to 4. x1, 4. x1, 4 less than or equal to x, I'm going to jump around, x2, 5 less than or equal to 3. And you do all 17 of these. And that's the end. You got it. All right. How are we doing on time? Because I know you guys are dying to talk about those. Just checking. All right, let's go back to the story. This company ships things all over the place. They use planes. They want to see what would be the maximum that they could ship indirectly from San Diego to Tampa in case that plane that goes from San Diego to Tampa breaks down. It would have to go through Denver. We have planes going to Denver, St. Louis, there's Dallas, Houston. They have to go all over, but they'll eventually get to Tampa. They want to know the different, here's the indirect routes from San Diego to Tampa with all the different, along with their respective estimated excess shipping capacity measured in hundreds of cubic feet per day. Almost all trucking I've ever experienced goes with cubic feet of space. When we did our trucks at our teaching industry, we weren't just counting the space at the bottom of the truck, we're counting the space all the way up to the ceiling. We would have these packed. Engineers would literally say, we know the dimensions of every package, and we would want it packed with the heaviest ones on bottom, the lightest ones on top, but we have figured out a way to pack it almost all the way to the ceiling. And your last delivery is packed first in the front of the truck, then your second to last delivery is packed to the ceiling, and then next. Your first delivery is in the back of your truck. The truck heads out, all the items are in order from your first delivery to your last delivery. So that's how it works. It's all on cubic feet. Here is our drawing. We know that these are our routes, and We went through this. We counted everything. Here's our objective function, one variable. Here's all our constraints, all equal to 0. Oh, we didn't do constraint 4, did we? Look at this. This one is showing everything going in as negative. We had everything going in as positive. Doesn't matter. They're both right as long as you're consistent. Look at 4, though. Negative x1, 4, negative x2, 4, negative x3, 4, negative x5, 4, negative x6, 4, plus x x42, x43, x45, x46, x47 equals 0. Again, these can be in any order. It's just a matter of making sure which ones are positive and negative, and then you're consistent. And then we plug it in. There's all of our arc constraints. These are, you've never had these in any of the other 4 from this chapter, only this one. My question for you is, how many, this is in thousands, how many thousands of cubic square feet can we get to Tampa if our plane breaks down through the alternative routes? 10,000, it's in thousands. That's the most we can get shipped. If that plane breaks down, that usually goes directly to Tampa from San Diego, we could go the alternative routes, but that's the most that could be shipped is 10. You can almost see, where am I at here? And it looks like, where's, all right, 10. That's about enough. All right, one more. One more. We're going to go to problem 32 on page 307. Not one more, just one more max flow. I want to make sure you guys get this. You have a max flow in your future sometime. If it's not on this quiz, it's going to be on your final for sure. Again, this is very commonly used. Like I said, detours. It's the maximum we can get through the opposite end through alternative routes. What they're doing on road construction is they say, okay, we know that 10,000 cars past this point, and so from this time to this time per day or something. So we know if we're doing construction for a week that we have this many cars averaging per day, that we have to find an alternative route that can handle that many cars. And so that's where they go into these constructions. We're doing this one right here. We're doing that one. Give me the objective function. Max. 7-1. X 7-1. Don't forget the X. X 7-1. There it is. Let's do node 3. Hang on, let me get a good pen here. Node 3. Do we want to stay consistent, or can we go ahead and do the opposite this time, just so we can see the opposite? Stay consistent. Okay. All right. Node 3. So we're starting with the positive ones, which will be going into 3. Help me out. X 2-3 plus X 5-3 plus X 6-3 plus X 4-3. Should I keep going? Is there more? 1, 2, 3, 4 going in. Minus X 3, 2. Minus X 3, 5. Minus X 3, 6. Minus X 3, 4 equals 0. There's constraint 3. It's that easy. You guys, if you don't ace this quiz, I'm going to be pissed.
You just said it was the hardest.
Oh, good point. You still got to ace it. All right. I think that's it. How many? Give me one of the alternative constraints that are not. This is the only one that doesn't have no. That has alternative constraints, not a no constraint. Tell me which. Give me an X. Any X as an alternative constraint. X what? 1, 2, 1, 4, 1, 2. Okay, 1, 4. Then what do I put? Less than or equal to what?
6.
So everybody get that? They looked at this one. They knew they had to do an arc constraint because this is max flow and it's not in the objective function. X 1, 4 less than or equal to 6. X 4, 6 less than or equal to 1. X 3, 5 less than or equal to 2. Everybody get that? Mm-hmm. Those are all the alternative constraints that you have to do. Objective function, we talked about one variable, blah, blah, blah. And now, hang on a minute. And now, my question, I don't have a question. I'll show you the official answer. There's the objective function, max 7-1. There's all these. There's all those. And this is posted on Blackboard. The Excel that we did with the subcontractors going to those projects are posted on Blackboard. The Excel we did for shortest route, posted on Blackboard. I also put 5 answers on Blackboard. The answers to one problem from the back of your chapter from every one of these examples. 1 transportation, 1 assignment, 1 transshipment, 1 shortest route, 1 max flow. They're all posted.